Yeah, I was sitting watching that last session thinking, I really feel sorry for the guy that's about to follow that before I'm realizing. And my other problem with the last talk is I'm kind of here to talk about engines, so and not at all about data. I work for a company called Quorum, and we do a lot with kind of data platform technologies, and it's more traditional analysis services. And what I'm going to talk today about has been more of a hobby of mine over the last kind of year or so. It started when I did a master's degree in data science at Dundee, and actually there's a few people, show of hands, that have also been or have done the course. And I would say if you're thinking about data science as a subject, it's a really great distance learning kind of course, and I would encourage you, if you see the strange man that looks like someone from a Harry Potter wizard, then grab him because he's the professor of the course and he's here today. But my final year project was to build a reinforcement learning AI influenced by the techniques from DeepMind AlphaGo. I obviously didn't have access to the full Google Cloud platform to be able to build something at the scale of DeepMind, but it did manage to achieve an equivalence with the top 100 human players in the world. So it was a reasonable attempt at a reinforcement learning algorithm. So today I want to talk about a brief intro to reinforcement learning concepts. Quick show of hands, has anyone done anything with reinforcement learning before? Okay, so a few people have done it, but most people are coming from, I guess, a low starting point. I'm going to talk about Monte Carlo learning, which is a simple technique really to illustrate here are the techniques and principles that you can use to train a reinforcement learning algorithm, and then move on to talk about how you can combine that with neural networks. So how can you use a neural network to drive a decision within a reinforcement learning scenario? There are some issues with reinforcement learning, particularly with deep neural networks. I'm going to talk about what those issues are, and then what the recent work by DeepMind and AlphaGo has been to tackle some of those issues. So what is reinforcement learning? Well, it kind of sits, there are three kind of core types of machine learning. So starting with supervised learning is where you take a big data set, so you give lots of examples of, here's an apple, here's an apple, here's an apple, and maybe some counter examples. This is definitely not an apple. And the reinforcement learning, the kind of machine learning algorithm basically looks at all these examples and it tries to work out what makes up an apple. Unsupervised learning is where you don't really know what you're looking for, but you're looking for interesting patterns or interesting clusters in your data set that an algorithm could identify. So it's quite often used in customer segmentation or potentially kind of fraud investigation or fraud classification, where you're looking for strange patterns in data. Reinforcement learning is the kind of third type of machine learning, and it's quite different from the other two. And it's based on some form of agent interacting with an environment and getting a reward signal as feedback. And that makes it quite different. And actually, it's very similar, and the previous speaker spoke about this, very similar to how you would train a dog. In fact, the RSPCA say that all training should be accompanied by a reward mechanism. So if I want to teach my dog how to fetch something, I'll maybe get a toy and I'll throw it, and the dog will run after the toy generally, or pick it up, and quite often it will then just go wandering off. But if I keep repeating this process, eventually the dog, by chance, comes back to me, and at that point, I give the dog a treat. I say, well done, pat, here's some kind of sweet or reward. And the dog starts to learn to associate carrying out that action with a particular reward that it gets. And that makes it more likely that it will do that action again. And that's really the concepts behind reinforcement learning. So within a machine reinforcement learning scenario, you have a number of components. So first of all, you have an agent. So an agent is a thing that is interacting with the environment. And the agent is in a particular state, and it takes an action in the environment based on its policy. So it has a policy which drives the decisions it makes. The environment then tells the agent, okay, you've made that move, you've stepped to the right, you're now in a new state, and potentially you now get a reward as a result of carrying out that action. You might not get the reward straight away. What you might get is the reward at an end of a number of episodes. So a game of chess, you don't get a reward until you've either won at the end of the game or you've lost. But other types of scenario, you get a reward as you go along. So what is a reward? Well, a reward, again, in machine learning, is a scalar feedback signal. And all that means is it's a number. So you need to come up with a single number that tells the algorithm how well it's doing. So that could be the amount of money won or lost within a poker scenario. That could be just whether you won or whether you lost in a chess game. Or it could be a combination of a series of potential actions. So, for example, my Terminator robot here, if he kills John Connor, he's going to get a huge reward. But he's going to get a negative reward every time he takes a step, because what I want him to do is kill John Connor in the least number of steps. You need to be really careful how you construct your reward mechanism, because if this agent here decides it's more than 10,000 steps to reach John Connor, what's he going to do? Well, he's probably just going to stand still and not bother taking any steps, because that's the way to maximize his reward. And that actually happened recently, well, not recently, a few years ago, with a Tetris-playing robot, where it decided just before it got to the top of the screen, it would pause the game and stay there indefinitely, because that was the way to not get that huge negative reward at the end of the episode. The agent itself generally has three components. So it has a model, and that's a representation of the environment. I'll talk a little bit about each of these. It has a policy, which derives, this is how I'm going to behave within that environment. And it has a value function, and the value function is how much reward am I going to get for carrying out a particular action. So the environment can be a visible environment. So chess is a perfect information game. Both players can see the entire board, the entire game set, what the opponent is doing, or certainly the position the opponent is in. Poker is a partial information game where actually you can see your own hand, but you can't see the hands of the other players. So the agent needs to build a model of what it believes are likely scenarios when it's playing this game. And likewise, some kind of self-driving car, it doesn't have a full model of the entire globe that it's driving around in. It builds a model that represents, potentially, the geospatial coordinates it's in, together with maybe some local sense of what lane the car's in and what other cars are kind of doing. So the agent has a model that represents the environment. The value function, according to Sutton, and Sutton's written one of the seminal books on reinforcement learning, is potentially the most important part of any reinforcement learning algorithm. And essentially, the value function tells the agent how good a particular state is or how good carrying out an action is. So why is that the most important part of a reinforcement learning algorithm? Well, let's say in a chess game, you have a value function that says how good a particular position is. So I'm not a chess expert, but this position looks pretty good for white. I might say from here, I've got an 80% chance of winning the game. Now, if I had a value function that could absolutely accurately estimate what my chance of winning from a particular position is, all I have to do is now look to the next possible move, what are all the possible positions, and I pick the one that's got the highest value. So if I have a perfect value function, I can essentially look at all the possible outcomes of my next move, pick the one with the highest value, and that essentially is the best possible move in this scenario. And that's called, in reinforcement learning, the optimal policy. So the value function is key to a reinforcement learning algorithm. But how do you actually estimate this? So I'm going to talk about Monte Carlo learning as a technique for this. And I'm going to use an example of noughts and crosses, or tic-tac-toe, if there's any Americans in the audience. And what I'm going to do is play a huge number of games completely at random. And in each game, I'm going to look at the move I took from a particular state and whether that move led to a loss or a win. And that gives me an idea of how good that move is playing against the random opponent. And this is called the evaluation step. So here is the first move of a tic-tac-toe board. And I could move to any one of these 9 squares. But I see, and this was taken, I took about 1 million games at random. 0.48 is my average return from the center square. And all that means is if I win, I get a 1. If I lose, I get a -1. If I draw, I get a 0. So 0.48 means 50% of the time I'm getting a win from picking the center square against a random opponent. Once I've picked that, it's the opponent's move. And the opponent now, if you look at the chances, again, playing completely at random, for a start, he's not going to do very well wherever he picks. But if he picks an edge square, he's going to do worse than if he picks a corner, where his average reward from there is negative 0.41. That's looking at it in terms of action values. You can also look at it in terms of state values, which basically says how good is it to be in a particular state. So from here, playing against a random opponent, I get a 41% win rate. Now I think anyone that has played noughts and crosses before will recognize that these probably represent sensible moves. So I can now use this to create a policy. So the policy now, what I want to do is say, well, actually, I want to pick the move that's got the highest kind of value. My opponent wants to pick the move that's got the highest value. And I'll play some more games, but using this as my policy. And so round 2 is, I do the same process, but with the new policy. And this policy is now showing, well, I'm actually winning far less games because the opponent kind of now knows how to anticipate my moves. But still, the center square is pretty good. And actually, if I then respond on an edge square, I'm going to lose most of the time. Can anyone see a slight, I guess, cheat that I've applied here, or something that's not quite consistent? Because the reality is, if I followed this policy greedily, I would always pick the center square. The opponent would always pick one of the corners, and I would never see how good these other positions are against this policy. And what you need to balance when you're working with a kind of reinforcement learning algorithm is what's called exploration versus exploitation. So I haven't always picked the center square to start with. Just very occasionally, I've tried one of the others to see what happens if I do something different. And this makes sure I keep exploring this state space as my policy improves. And the technique I've used for that is called epsilon greedy learning, which is probably the simplest way of doing this, and probably also one of the best. And all it says is, with some probability, I'll say 90% here, I'm going to make a good move. But with a 10% probability, I'm going to make a move completely at random. And then as I do subsequent iterations of this policy, I reduce this epsilon number. So I'll go from 10% to 9 to 8, until eventually I end up at the optimal policy. And this is the core principle of reinforcement learning. You start with some policy, maybe completely at random. You evaluate the policy. You see what value function that policy produces. And you use this new value function to then define your new policy. And that's your policy improvement step. And you then repeat the process. And eventually, with techniques like Monte Carlo, and there's a whole other series of classes of algorithm, these will converge to the optimal policy. That's all very well with noughts and crosses, where I can build an array, and there's only 20-odd thousand action values that you can take in a noughts and crosses game. But what about when you get a huge state space? So chess has about 10 to the 47 states. Go has 10 to the 170. So Go is very much a much, much more complex problem to solve than chess, which kind of got beaten in the Deep Blue era through very much a brute force kind of approach. To do this, we need some form of function approximator. And actually, neural networks are one of the best function approximators that we have these days. So how does this work? Basically, I'll take a chessboard. I'll then come up with some kind of encoding. Now, this could be a different layer for each type of chess piece, which would be the normal approach. I've just shown a simple example where the pieces all have different values. And then I'll flatten this board out, and I'll feed that into some kind of neural net. And from there, I'm now going to apply the same techniques that I've applied in the previous example. So essentially, what I want to do is say, well, from this position, I'll play through using my policy. Did I win or did I lose? And if I win, this board position, together with the result, becomes a data point that I feed into the neural net, so it can start to learn what's a good position versus what's a not so good position. So it's exactly the same principle as we apply with tic-tac-toe. Start at random, play a bunch of games, record all the board positions and whether they led to a win or led to a loss, and then you use that to feed into your neural network to produce your next policy. Deep neural networks have been, revolutionary, I think, across kind of the world of kind of deep learning. But they don't work, or they haven't historically worked well with reinforcement learning. So this was the first thing that people said, well, let's try and apply deep neural networks to reinforcement learning, and it just never worked. And there's a few reasons. I mean, inherently, a deep neural network is quite unstable. And two of the main ones that happen when you're applying deep neural networks to a reinforcement learning scenario is you get correlations between a sequence of observations. So if I'm trying to follow a policy, so I have a neural network that's defined my policy, maybe I'm playing some kind of Atari game, Kung Fu Master. I've got to the third level. I'm moving to the right. I'm hitting all the bad guys. The network starts to get feedback based on what it's currently doing, and it starts to forget what it did in level 1. And actually, when you then go back to the first level, it's suddenly forgotten how to play. But also, if you're updating the neural network as you go, you can get just instabilities because these things are quite unstable kind of by nature. So as you update it by a small amount, it significantly changes the policy, and it suddenly starts losing. So we needed a way of stabilizing these networks. And there was a very interesting paper from DeepMind back in 2015, which basically looked at a whole bunch of Atari games. I think there was about 20. And it used two new techniques. It used a thing called experience replay, and it used a thing called a target queue network. And the output of this was it achieved above human level in over half the games. And this was quite a revolutionary paper. And this really has changed. And I would advise that these papers are all available through Nature. They're quite a good read, so I've got some links at the end. And what it did was it basically took the screen from the Atari game as the input. It ran it through a couple of layers of convolutional network, fed that into a kind of deep feed-forward network, and then used that to predict whether this kind of position should move to the left, right, or press the joystick button. So how do these things work? So for a start, it's similar to what we spoke about before. The agent has a policy, it interacts in the environment, and it gets some kind of reward signal. But instead of using that reward signal to update the agent in a traditional reinforcement learning, it stores this. So it stores the state it was in, the action it took, the reward it got, and the state it went to. And it stores this into what's called a replay buffer. And I think the replay buffer for Atari was about 1 million kind of nodes long. So this goes right back. And instead of directly updating from what just happened, they create a new copy of the agent, and this is to solve some of the stability issues. And the agent samples from the replay buffer. So it will pick a couple of hundred examples at random of things that it did and what the outcome was and what the reward was from maybe the last game, maybe 100 games ago, maybe what it's just done. And this helps stabilize it because it's kind of like saying, well, from this position, that was a good thing to do. From that position, so it's not focusing the learning on what it's currently doing. It's focusing the learning across a wide range of experience. And there's been some studies that show this is kind of what humans do when they dream. You're kind of consolidating what has gone on over the last day, over the last week, what happened last year. In kind of some way, that is how the human brain kind of learns from experience. Once you've updated this new agent a number of times, a few hundred kind of episodes, you then may decide to swap them out. You might have some kind of criteria. You might say, well, let's actually, before we swap these, let's play them against each other and see which one's better. But at some point, you then swap, and then you repeat the process. But you're still learning from what the previous version of the agent did. So again, you're not just impacting your learning based on the current agent. You're also looking at, well, the previous agent did really well in this scenario. I'm learning from that experience. And the difference between, so if you look at the stats of Breakout, it was getting a score of around 3. With the replay learning and target queue networks, it got a score of about 300. So this significantly made a difference in the ability of these networks to learn. I suspect a few people saw the news about Go when AlphaGo beat the world champion, Lee Sedol. And AlphaGo, again, took these deep queue networks and applied it to a field that I think people were skeptical was going to be solved in the next 10 years. And the initial version of Go was trained on a database of human expert games. And then it played itself. And it played itself for, I think, about 3 to 4 months before it then played Lee Sedol. And there's a great Netflix documentary, if you've not seen it, called AlphaGo, which kind of shows the history of some of this. Following that, they actually came up with AlphaGo Zero, and they started again, but this time they didn't start with a database of human games. They started with random play, again, like we did in the early scenario. And within 36 hours, this new version beat the previous version 100 games to 0. And David Silver's quoted as saying, every time you put knowledge into a system, you're actually handicapping it. And I think the reason for this is humans tend to think that they know better than the machine. So you might think that with a chess-playing algorithm, well, I know a pawn's worth 1, and I know a knight's worth 2, and I know a queen's worth X. But those are human-invented constructs, and the machine can actually come up with better kind of versions of those if you let it. So AlphaGo Zero basically just uses the board position as input. It uses a Monte Carlo tree search, and that's, I'll talk a little about what that is, but it's a way of kind of looking ahead and then seeing how good a position you could end up in, and then using that to update kind of where you currently are. It moved from a convolutional network to a residual network. So a convolutional network scans the board kind of in sectors, but then it builds up a hierarchy of kind of features to kind of then make decisions from. A residual network does exactly the same, but it has kind of links back to the layers below. So essentially, you get a kind of high-level abstraction together with a much more detailed view of what's happening on the board. And they also had, which I've never seen before, a dual-headed network. So the board position was the inputs. The output was actually 2 different values from the neural net, one being what move it thought was likely, the other being what strength does it think the current board position is. So actually, it's the first example I've seen of a neural network that actually has 2 outputs that are both trained separately. The tree search basically starts at the position it's in. It looks ahead, so it says, OK, what are the most likely moves? And it samples from them based on how likely they are. And it does that several nodes deep. And then it works out what's the strength of the position I get to at the end. And then it uses that strength to update how strong it thinks the current position is. So if it thinks my current position is 70%, but I then look a few moves in terms of what's likely to happen, and I'm now somewhere that's kind of now an 80% chance of winning, do you know what? I'm probably closer to 80% back where I was. So it's a way of looking ahead, but then using that look ahead to update the value of where you are. So it's kind of almost building future kind of view into the network itself. What I don't know if anyone else has seen or everyone's seen is they took the same network and the same design and they fed it chess. They just gave it the rules of chess. And within 4 hours, it beat Stockfish, which is the world's best chess engine. And within 2 hours, it beat the best shogi kind of game in the world. So what they've managed to create is a generic algorithm. I like to think of it as a big jet engine from the previous talk. But this is an algorithm that really can be applied to multiple different scenarios and kind of learn them from scratch. I did do some digging on the 4 hours because I thought, well, that's incredible. It was running on 5,000 tensor processing units for 4 hours. And you kind of think about that and you think, well, that's resource I don't have. But if you look at it in terms of the cloud and what's available kind of out there, certainly on public cloud platforms, that would represent about £40,000 worth of cost. So if you have an algorithm and you've got a reasonable budget, you can create a world-class engine to play pretty much anything. And it's not a huge amount of money if you consider how much a development team to create shogi probably cost, over tens of years of development. 40 to 50,000 is not a huge amount of money. So I've got a question, and I think certainly a couple of talks have asked this. In reinforcement learning, what's more important, the data or the algorithm? Show of hands for data. Algorithm? Yeah, and I think one thing that this has shown is the algorithm can pretty much be applied to any scenario and learn it. And with reinforcement learning, you haven't got much in the way of data. You're generating the data as you go. And to some degree, that's why I picked a reinforcement learning project for my master's project, because I don't trust anyone else to give me a decent data set. So I thought I'll do something where I'm generating my own. What? Lazy. Thank you, Dominic. So to kind of summarize in terms of the concepts we've talked about, value estimation is absolutely critical to reinforcement learning. Monte Carlo learning is kind of one example, and it's a good technique to kind of play with and kind of get some exposure to what reinforcement learning can do. It tends to be a little bit more stable than what's called some of the bootstrap methods like TD Lambda, etc. You need to make sure you balance exploration versus exploitation, i.e. still taking some random moves rather than always trying to follow the optimal policy. Obviously, if you build a reinforcement learning to play a game, when you're playing the game for real, you want to use the greedy algorithm. You want to take the best moves in every scenario. But when you're learning, balanced exploration is key. And if you are going to play with deep neural networks, the only advice I can give you is be careful, because they are very, very unstable, and you will spend weeks just saying, why is it not doing anything at all? Experience replay can really help with that. Finally, just talk about what next with reinforcement learning. And within the gaming community, the target is now much more complex games. So No Limit Texas Hold'em has just been cracked, where an AI beat a team of professional kind of world champions at poker. StarCraft and Dota 2 are quite complex strategy games that, again, are now above human level in terms of ability. And there's a project, while I was researching for this, I came across called OpenSpiel, which is a DeepMind GitHub library. And basically, it's DeepMind open sourcing a lot of the techniques that they use to build the AlphaGo kind of project. So there's about 20 board games that have been defined there: chess, Go, backgammon, shogi, etc. and a whole bunch of algorithms you can use to actually do reinforcement learning on and frameworks. So it's a great kind of resource and tool set. I would encourage, if anyone's thinking about doing a reinforcement learning project, have a look at that before you do. But ultimately, I think these are test beds for these companies, but the plan is to start applying this to real-world scenarios and actually solve some of those kind of world problems that were discussed earlier. So energy efficiency, I know that the Alpha kind of Go reinforcement learning has been applied to running Google's data centers, and they've achieved about a 30% cost saving. And data center energy is currently about 3% of world energy consumption. So that's quite a big win if you can start applying to those scenarios. But there's a bunch of other areas. Self-driving cars, protein folding, which again has dramatic kind of possibilities in the world of medicine, materials research, smart materials, and eventually you can't have a kind of talk in this kind of place here without mentioning artificial general intelligence. And I think whether or not that's possible, it will certainly demand some concepts of reinforcement learning to come up with what I would call an AGI. There's a few references. I think the slide decks are getting published online. So a few references, the Netflix documentary. There's a great course by David Silver of DeepMind on reinforcement learning from UCL. I would really recommend kind of watching that if you're interested. There's a free book. It's free kind of online by Sutton and Bartow on reinforcement learning. And then there's some great kind of Nature papers which the Google team have released. And I think that's all. Thank you.